Hello, everyone, and thank you so much for being here today. When we talk about AI, a lot of the excitement sits around the models, the possibilities, the breakthroughs, and the things we can now build that felt impossible to build a few years ago. But underneath all of that magic is a very real layer of engineering that keeps everything running. Today, we're going to spend some time talking about that layer. We're going to explore what it really takes to manage cloud infrastructure when AI systems become large, demanding, and deeply integrated into a business. I'm excited to walk through this with you. My name is Adora Nwodo, and I spend most of my time thinking about cloud infrastructure, platform engineering, and how teams build reliable systems at scale. I've worked across large engineering organizations, I've built tools that support developers, I've written books on cloud technology, and I've spent a good part of my career helping companies design platforms that actually grow with their needs. I care about this topic because I've seen what happens when teams try to scale AI without a strong foundation. The excitement is there, the ambition is there, but the infrastructure underneath starts to crack. And I've also seen what's possible when the foundation is solid. So today, I'm here to share lessons, patterns, and real human insights from those experiences. When you look around today, it feels like the whole world is running on excitement about AI. Every week, there's a new announcement, a new capability, a new you wouldn't believe that this model can now do this moment. And honestly, it's inspiring to see how quickly things are moving. Teams everywhere are experimenting, companies are inventing old processes, and entire industries are rethinking what's possible. But when you peel back all that excitement, something very real is happening behind the curtains. As these AI systems grow, the conversation quietly shifts. It stops being just about the model themselves, or the research breakthroughs, or even the clever prompts. It becomes a conversation about the foundation holding everything up. Because here's the truth people don't talk about. The moment an AI system stops being a fun experiment and starts becoming something a business actually relies on, the pressure on the infrastructure multiplies. Suddenly, it's not just one model training on someone's laptop, it's a cluster of GPU machines running distributed jobs. It's not just a dataset stored somewhere, it's petabytes of data being streamed, processed, cached, moved, and accessed constantly. The stakes get higher, the demands get bigger, and the systems underneath start feeling the weight of all that ambition. And that's really why we're here. The future of AI isn't just about intelligence, it's about the plumbing, the scaffolding, the groundwork that lets these models thrive in the real world. If the infrastructure isn't right, nothing else works. And if it is right, the possibilities open up so much faster. So, on this journey today, I want us to step back from a hype a little bit and really look at the invisible layer that makes everything possible. Let's talk about what happens behind the scenes when AI becomes large, demanding, unpredictable, and maybe embedded in a business, because that's where the real story is. One thing I've realized over the years is that AI workloads don't behave like the systems most engineering teams are used to. When people talk about cloud workloads, they picture web apps, APIs, maybe some background jobs here and there. Those are predictable. You scale them horizontally, you manage your traffic patterns, you set up health checks, and most times they behave. AI workloads are not like that. When you start working with large models, everything becomes amplified. The compute requirements jump dramatically. Suddenly, you're talking about GPUs, TPUs, specialized accelerators, and clusters that operate like small cities. Training a model isn't just run this job, it's distributed computation running across dozens or hundreds of nodes, all needing to communicate fast enough to stay in sync. And then you add data into the picture. AI doesn't nibble data, it devours it. It needs high throughput storage, it needs proximity, it needs the right format, and it needs it constantly. If the data pipeline hiccups, the entire training job can stall or even fail. And with the cost of GPU time, you don't want to waste even a minute. Another thing that makes AI workloads unique is the unpredictability. The patterns can be strangely busty. One day, you are running a training cycle that eats every resource in sight, and the next day, you are running lightweight inference tasks. Some teams ramp up massively for experimentation, and then everything goes quiet until the next cycle. Traditional auto-scaling strategies would fail here because the demands come in waves, not steady lines. So when we think about managing cloud infrastructure for AI, We have to rethink everything we know about scale. We can't assume predictability. We can't assume uniform workloads. We can't assume that standard compute strategies will be enough. AI forces us to design systems that can handle intensity, speed, and chaotic patterns without collapsing under pressure. And that's why we need a different mindset, a different set of tools, a different way of thinking about cloud architectures. Because the moment someone says we're building something with AI, the infrastructure story changes completely. One thing people don't always realize until they're deep in the journey is that scaling AI comes with a hidden cost. And I don't just mean money, although trust me, the money part gets very real very quickly. I'm talking about the operational strain that slowly creeps in the moment your AI ambition starts growing. In the beginning, everything feels exciting. The team is experimenting, building prototypes, running small training jobs. Everyone is optimistic. The models are promising, and you're dreaming about what the system could become. But then, almost quietly, things start to change. The number of experiments increase, the data sets get bigger. Someone decides to start trying a larger model. Someone else wants to run a hyperparameter sweep. Suddenly, your cluster usage spikes, you are scrambling to find available GPU capacity, and your cloud bill starts looking like a phone number. You start seeing resource sprawl. Machines you spun up for a quick test are still running 2 weeks later. Pipelines that were fine at 10 gigabytes break completely at 200 terabytes. You still have scheduling conflicts because everyone wants GPUs at the same time. Something that works perfectly in development now takes 20 minutes just to load data, and the beautiful architecture diagram you had at the start, it slowly stops matching reality. And then there's the human side. Engineers begin fighting for compute slots, training jobs get killed midway because someone needed the cluster urgently, people start running experiments in the middle of the night, hoping they can catch some free GPU time, and your team that used to move fast suddenly starts slowing down because the infrastructure can't keep up. These are the hidden costs. The chaos, the inefficiency, the time wasted, the stress no one talks about during the hype conversations. AI at scale is powerful. It's transformative, but it puts pressure on every part of the cloud stack. And if you don't get ahead of that, the cost isn't just financial, the cost is velocity, the cost is reliability, the cost is the team's ability to keep innovating. And that's why managing infrastructure isn't just a technical necessity, it's a survival skill for teams building serious AI systems. When you look at a large scale AI system from outside, it feels like one smooth thing. You send data in, a model trains, predictions come out, and everything feels like magic. But when you step in behind the curtain, you quickly realize that these systems are not one thing at all. They are an entire ecosystem of moving parts that have to work together, almost like an orchestra. Let me paint the picture. At the very bottom, you have your data pipelines. These are the arteries of the whole system. They're pulling data from different sources, cleaning it, transforming it, validating it, enriching it, and preparing it so your models aren't learning from chaos. If this layer is weak, the whole system becomes unpredictable. Sitting next to that, you have storage, not just any storage, but specialized, high throughput, high availability storage that can handle massive reads and writes without slowing everything down. AI doesn't wait patiently, it needs data immediately, and it needs it in huge volumes. Your architecture has to support that pace. Then you have the brain of the operation, the training clusters. This is where you see distributed training, GPUs, accelerators, schedulers, and orchestration tools working like a busy airport. Jobs are coming in, nodes are communicating, workloads are syncing gradients across machines, and everything has to run without falling apart. One slow node can drag an entire training job down. On another side of the ecosystem, you have your inference layer. This is where the trained models actually serve real users or other systems. Sometimes this happens in low latency environments. Sometimes it needs massive horizontal scale because traffic arrives unpredictably. But either way, your inference architecture has to be fast, resilient, and cheap enough to run continuously. And then, hovering above everything, you have your observability and monitoring loops. This part is often ignored until it's too late. You need full visibility into every part of the stack: GPU utilization, training metrics, cluster health, data throughput, inference latency, anomalies, and even user behavior. Without full visibility, you are running a very expensive system, very blind, and that can be chaotic. When you zoom out and look at all these layers together, you start to see the truth. Large scale AI isn't just about models, it's a complex interconnected architecture that requires thoughtful design. Every layer affects the next. If one layer is slow, the whole system feels slow. If one layer breaks, everything breaks. So before we talk about optimization or cost or scaling strategies, it's important to understand that you are actually building something. You're not just deploying AI, you need to know what you're actually building. You're building an entire ecosystem, and every part of it has to be strong. Now that we've painted a picture of the ecosystem, let's talk about the foundation it all sits on. Because the truth is, before you even think about GPUs or distributed training or real time inference, the first big decision you make is the cloud foundation itself. And that choice shapes everything that comes after. When you're supporting large scale AI, you're not just spinning up virtual machines, you're making decisions about the backbone of your entire system. You're choosing the regions where your workloads live, you're defining how your networks are structured, you're deciding how data moves, where it's stored, and how fast different parts of the system can talk to each other. Your compute layer becomes especially important. You're thinking about whether you need on demand GPU capacity, reserved capacity, or a hybrid approach. You're thinking about the availability of accelerators in specific regions. You're thinking about proximity between compute and data. AI workloads are incredibly sensitive to latency in ways typical applications are not. Then there's your storage. You need to understand the performance guarantees of each storage tier. You need to understand how your data will be accessed during training versus inference. You need to understand when to use object storage, when to use block storage, and when to use a parallel file system, and how to design something that wouldn't buckle under pressure. And of course, there's the network, the silent force behind absolutely everything. With AI workloads, the network becomes one of the most critical components because so much of training and inference depends on fast, reliable communication. Every millisecond counts when nodes are trying to synchronize gradients or stream large batches of data. What's interesting is that none of these decisions exist in isolation. Everything influences everything else. Your compute choices influence your storage strategy. Your storage strategy influences your network layout. Your network layout influences your job scheduling approach. It's all connected. So choosing your cloud foundation is a very strategic choice. It's one of the earliest decisions that determines whether your AI systems will scale smoothly or struggle as they grow. It's part of the journey where you pause, take a breath, and intentionally design the ground you're going to build on. Because once the workloads start increasing, once the models get bigger, once the organization starts depending on AI, it becomes much harder to fix the foundation beneath a system that's already in motion. When people think about AI infrastructure, they often jump straight to the compute layer. And honestly, it makes sense. Compute is where all the visible action happens. It's where the model trains, where the accelerators work over time, where the real heavy lifting occurs. But what many teams don't realize is that managing compute for AI isn't just about having powerful machines, it's about balancing availability, efficiency, cost, and predictability in a way that keeps the entire system healthy. GPUs and accelerators are the heart of AI workloads, but they are also one of the most scarce and expensive resources in the cloud. So the moment your organization starts scaling AI, you feel every decision around compute very deeply. You are deciding when to use on-demand GPU instances, when to rely on reserved capacity, when to leverage spot instances, and when to borrow compute across regions if your primary one is saturated. Then there's the orchestration layer, which becomes a whole world on its own. You need a way to schedule training jobs so that the cluster isn't overloaded. You need to make sure that distributed training nodes start correctly, start synchronized, and don't bring everything down because of one slow or failing machine. You need policies that determine which workloads get priorities so that your most critical experiments don't wait in line behind routine tasks. Another challenge is making sure your compute layer can scale. There will be weeks when the team is running extremely heavy workloads and weeks where everything is quiet. Your infrastructure has to be ready for both. And unlike traditional web applications, AI workloads don't scale gradually, they scale in sudden spikes. Someone launches a training run and suddenly everything needs to expand. Teams often underestimate how quickly compute weight accumulates. GPU nodes that aren't shut down after a job, misconfigured training jobs that silently burn through hours of compute, idle nodes waiting for someone to connect to them. In an AI environment, these small mistakes turn into real costs extremely fast. And when your models are running for days or weeks, every inefficiency becomes expensive. So managing compute for large scale AI becomes a story of discipline, a story of building the right automation, the right scheduling strategy, the right policies, and the right culture around using compute responsibly. Because in AI infrastructure, compute is the pulse of the entire ecosystem, and the way you manage it determines whether your AI platform feels smooth and empowering or chaotic and unpredictable. Now, let's talk about the storage story. Because when you're building these systems at scale, storage is one of the things you don't think about at first, and it suddenly becomes the thing you think about all the time, right? It sits quietly in the background, but it influences absolutely everything: how fast your models train, how reliable your pipelines are, how often your jobs fail, and even how much you spend. AI doesn't use data gently. It doesn't retrieve a few fields from the database or fetch small files occasionally. AI systems ingest data into massive volumes. They read constantly, they write constantly, and they expect storage to keep up without slowing anything down. So, the story of storage of AI really begins with understanding the nature of your workloads. Training jobs need high throughput and low latency. They need to read huge batches of data quickly. They need to be close to the compute layer so you're not wasting time transferring data across regions. Meanwhile, your pre processing tasks might need something more flexible and scalable, like object storage, because they are dealing with unstructured data coming in from multiple sources. Then there's the question of where the ground truth lives. You might have a master data set that sits in durable object storage, but when it's time to train, the data often needs to be moved or copied to a high performance format or storage layers designed for speed rather than durability. It's a balancing act between price, performance, and readability. Another piece of the storage story is versioning. AI teams generate so many variations of datasets: cleaned versions, augmented versions, filtered versions, labeled versions, all of that. And if you're not careful, you end up with a maze of inconsistent data scattered everywhere. This creates confusion, slows down teams, and increases the risk of training on outdated or incorrect data. And then there's the operational reality. If your storage layer is slow, your whole system feels slow. Training takes longer, pre processing takes longer, model evaluation takes longer, inference becomes unpredictable. A misconfigured storage tier can quickly add hours or days to your workflows without anyone noticing until the cost starts showing up. Storage is one of the few pieces of AI infrastructure that affects every single stage of the life cycle. It influences ingestion, transformation, training, deployment, and monitoring. It's not just where you put your files, it's the engine that feeds your models. So when people ask, what kind of storage should we use for AI? The answer is never a single service or product. The answer is a strategy built on performance, locality, consistency, and a deep understanding of how your data behaves as it moves through the entire system. Networking is also a very demanding thing when we're thinking about AI systems at scale. AI workloads are incredibly demanding on the network because so much of what they do involves constant communication. Distributed training is a perfect example. When you're training a model across multiple machines, those machines are exchanging parameters, gradients, checkpoints, and updates continuously. They're talking to each other non-stop. And if the network can't handle that level of traffic with low latency, the training job drags. Sometimes it even fails. The same thing happens with data pipelines. You are moving massive files around, you're streaming data into pre-processing steps, you are loading training batches from storage. Every small delay compounds into bigger delays, and before you know it, your entire workflow feels slow and unresponsive. And in AI, once a system starts feeling slow, the cost of running it skyrockets. Networking affects inference too. If your model is powering a customer facing feature, latency becomes a real concern. That round trip between your application and your model server needs to be fast. You might need private endpoints, dedicated interconnects, or region specific deployments just to get the performance level that you want. And this brings us to another challenge: geography. AI teams often have data in one region, compute in another, and customers yet in another. Every time data crosses the wrong boundary, you pay in latency, you pay in throughput, and sometimes you pay literally in cloud egress fees. So you need a strategy that keeps your workloads as close together as possible. Then there's the security layer. You're working with sensitive data, sometimes regulated data, and you might need private networking strategies that give you isolation without creating bottlenecks. You might need VNet pairing, service endpoints, private links, or specific routing rules just to make sure everything communicates safely and efficiently. The thing about networking in AI systems is that it isn't glamorous and it's rarely the first thing teams talk about, but it quietly shapes the success of everything else. If your network is strong, your training is smoother, your data pipelines flow faster, your inference responds quicker, and your costs stay predictable. But if your network isn't designed well, the team will always feel like it's dragging its feet, no matter how powerful your GPUs are. So, networking is a connective tissue that lets the entire AI ecosystem operate like one cohesive machine. And as usual, if you know me very well, you would know that I would always preach automation and infrastructure as code. With AI as well, right? As the systems grow, manual work will not cut it anymore, right? It's one thing to tweak a configuration or spin up a machine when the team is experimenting with a small model. But once you're managing clusters, pipelines, distributed jobs, and multiple environments, the smallest manual mistake can bring an entire system to a halt. One thing I always say, right, is that you can't manage what you can't see. And when you're dealing with large scale AI systems, this becomes even more true. These systems have so many moving parts: data pipelines, compute clusters, orchestration layers, training loops, inference endpoints, and they are all running at high intensity. If you don't have deep visibility into what's happening, you're flying blind. Observability in AI infrastructure is about understanding the health, behavior, and the rhythm of the entire ecosystem, not just the regular logs and metrics that we know about. You want to see how your GPU nodes are performing in real time. You want to know if your training jobs are progressing in the way they should. You want to detect bottlenecks early before they become outages, and you want to have enough historical data to understand long term patterns. Let's talk about training first. When a model is training across multiple machines, small issues can turn into huge delays. Maybe one node is slower than the others. Maybe the data pipeline isn't feeding the batches fast enough. Maybe a misconfiguration is causing memory spikes. Good observability lets you catch these problems immediately instead of discovering them halfway through a 72-hour job. Then there's inference. Your model is serving real users or real systems. You need to understand latency changes, throughput changes, error rates, and performance under load. Even slight increases in latency can cause a poor user experience or break downstream processes. You want to know when your model is drifting. You want to know when response patterns change. You want visibility into how the model behaves, both during quiet hours and during traffic surges. Observability also plays a huge role in costs. GPUs are expensive, storage is expensive, data movement is expensive. If you're not able to see how your infrastructure is being used, you end up with runway expenses without realizing where they're coming from. Observability helps you catch waste early and course correct quickly. And finally, there's the idea of understanding your system through time: how workloads evolve, how patterns shift, and how the system grows. When you can see your infrastructure not just as it is right now, but how it has behaved over days, weeks, or months, you're able to make better decisions, more informed decisions actually. You gain the intuition needed to design systems that get stronger as they scale. Observability isn't just a monitoring layer, it's the compass that guides every decision you make about your AI platform. It's the difference between reacting to failures and proactively improving your system. And when your infrastructure gets as complex as what I'm describing right now, That difference really matters. When AI systems start growing, one of the biggest challenges is keeping everything reliable. And I don't just mean keeping the servers up, I mean making sure the entire system behaves predictably, even under stress, even during peak demand, even when something unexpected happens. Because once AI becomes part of a product or a business workflow, any downtime becomes very visible very quickly. AI workloads push infrastructure in ways that traditional systems don't. Distributed training jobs can run for days, and one tiny failure in a single node can cause the entire job to crash. Inference systems can go from quiet to overloaded in seconds if a new feature launches or a sudden wave of traffic hits. Data pipelines can get backed up because one pre-processing step slowed down. None of these challenges are theoretical, they happen all the time in real environments. So, when we talk about reliability, we're talking about designing infrastructure that expects things to go wrong and is ready to recover gracefully. For training workloads, this might mean using checkpointing so that a job doesn't lose all its progress if a node dies. It might mean spreading jobs across multiple availability zones. It might mean designing your scheduler to automatically retry tasks or reroute around failing hardware. Scaling is another part of the story. AI infrastructure needs to scale in more than one direction. Sometimes you scale up vertically because a larger model needs more powerful hardware. Sometimes you scale out horizontally because you need more nodes to train faster. Sometimes you scale your inference endpoints because traffic patterns change suddenly. And sometimes you need the flexibility to scale down so you are not paying for resources you don't need. What makes scaling AI systems complicated is that the patterns are rarely steady or predictable. One day you're running a single long training job, the next day, 5 teams are launching experiments at the same time. The next day, you are hosting a model that suddenly becomes popular. So, your infrastructure has to be elastic without becoming chaotic, and it has to be dynamic without losing control. Security is also very important because apart from the regular security we think about from an application context, application security, you're also thinking about things beyond like APIs and access tokens. You're thinking about how access works here in terms of like who can access training data sets, where those data sets can live, how they are transmitted, and whether they are isolated properly. You're thinking about model integrity. You're making sure the model hasn't been tampered with or poisoned. You're thinking about the pipelines that feed the model and whether those pipelines can be manipulated, right? If you follow Microsoft's framework for responsible AI as well, there are a lot of security related things there, and you're also thinking about those things, right? Identity becomes a core pillar of the story. With Entra ID and other identity systems, you control who can touch what, not just at the application level, but all the way down to compute, storage, and orchestration layers. You want tight control on who can spin up GPU clusters, who can access datasets, who can deploy models, and who can modify pipeline configurations. AI systems attract a lot of interest, both from internal teams or from outside threats, so clear identity boundaries matter. Another layer is data protection. AI workloads often depend on large, rich data sets. These data sets may contain sensitive information or they may be proprietary assets that the organization can't afford to lose. Encryption at rest and in transit becomes non negotiable. Network isolation becomes essential. Even the way data sets are shared between environments has to be intentional. A simple misconfiguration can expose far more information than you want. Then there's the runtime side. Models serving in production need protection just like any other service. Rate limiting, traffic filtering, request validation, all of these still apply. But you also have additional concerns like model extraction attempts, adversarial inputs, and inference abuse. You want to be certain that your endpoints aren't being overloaded or manipulated in subtle ways. Finally, the integrity of the entire pipeline matters. If someone injects malicious data during preprocessing, the model can be skewed. If someone impersonates a service identity and modifies a training script, the model can be compromised. If pipeline steps aren't validated, you can end up deploying a broken model to production simply because the system assumed everything was safe. So you have to make sure that you are thinking about these things from a security context as well for AI infrastructure. When you step back and look at everything we've talked about today, a picture starts to form. Managing cloud infrastructure for large scale AI isn't just about one tool or one technique or one best practice. It's about building an entire ecosystem where every layer supports the next, where every decision reinforces stability, and where the entire system grows with the organization instead of working against it. You have the data pipelines, the storage layers, you have your networking layer, you have automation, you're thinking about observability, you're thinking about cost management, and then you have security as well. These layers come together to create something bigger than the individual pieces. They create a living platform that can evolve, adapt, scale, and support the rapidly changing needs of any AI development. And what's beautiful is that when everything works well, the complexity starts to fade away. The infrastructure becomes invisible. The teams don't think about how the data is flowing or how clusters are scaling. They just build, experiment, and ship. The system becomes the quiet force that makes innovation very possible. And here's the bigger truth: successful AI organizations aren't just good at building models, they are good at building environments where models can live fully healthy, productive lives. They're good at designing infrastructure that doesn't just handle scale, but actually accelerates the team's ability to create. So when we talk about managing cloud infrastructure for large scale AI, we're really thinking about designing a foundation for the future, a foundation that gives teams the freedom to imagine bigger things, try new ideas, and push the boundaries of what technology can do. And at the end of the day, really, ultimately, that is the goal. Not just to keep systems running, but to create an environment where AI can thrive and where the people building it feel empowered, supported, and ready for whatever comes next. And I've come to the end of my presentation. I really hope you learned a lot. Thank you so much for spending this time with me. I know that I said too much, but I hope that this journey made the whole picture a little clearer. Not just the technology, but the philosophy behind building infrastructure that genuinely supports AI at scale. If you'd like to learn more about my work, my books, or the things I'm building, you can always find me online. I'm active on LinkedIn, I'm active on X, and I'm active on Instagram. And you can find all these different links, of course, through my website and also my name. I am Adora Nwodo on LinkedIn and Adora Nwodo on X as well. Thank you once again for inviting me and enjoy the rest of the talk. Have a wonderful day.